Okay, ladies and gents, welcome to my box room. So I had a little bit of an issue with recording the last piece of notes. This is for week 10. Unfortunately, they were all completely blurry and I can't do them again, so I'm going to send them all on in a PDF, and just here we're going to explain what kind of just the big story. So basically what we're talking about, and the two problems that we're looking at are, you can look at this in the notes, you've got the first one is you've got two vats and they have salt in them, some salt, some water, and you have clean fresh water flowing into the first vat, coming out and going into the second vat, and then more liquid is flowing out. And the question is, how does the salt's concentration change in time? And basically what you have here is a differential equation relating two rates of change, the rate of change of salt in the first vat and the rate of change of the amount of salt in the second vat. And this is called the system of differential equations, but you can think about it as simultaneous differential equations. Now in the notes that I'm sending as a PDF, these differential equations are kind of, let me say, applied, but here I'm just going to do kind of look at it abstractly. So abstractly what we have is we have two differential equations, say dx dt equal to some constant times x plus some constant times y, and we have a second differential equation, say dy dt is equal to some other constant times x plus some other constant times y. So both of the applied examples in the notes are of this form. So these are simultaneous differential equations. You're looking for a pair of functions x of t, y of t that solve both differential equations. And this is a difficult problem. So that's the dog. What we're going to do is we're going to use the Laplace transform to turn these simultaneous differential equations into simultaneous algebra equations. So for example, if I take the Laplace transform of the first thing, I will get s times big X of s minus little x of 0 equal to, fix the a, little x of t is sent to big X of s, plus fix the b, little y of t is sent to big Y of s. And take the Laplace transform of the second one as well. So dy dt is sent to s times big Y of s minus little y of 0 equal to, fix the constant c, little x of t is sent to big X of s, plus fix the constant d, little y of t is sent to big Y of s. So what the Laplace transform does is it turns simultaneous differential equations into simultaneous algebra equations. What's missing here is that the initial condition of x will be given here. The initial value of x, say, is x0, and the initial value of y, say, is y0. Now, as I said, so these, now a, b, c, d are known constants. S is the s variable in the s domain, and x0 and y0 are numbers that we know. So actually the only unknowns here are big X of s and big Y of s. Now any simultaneous equation method that you have of attacking this is equally valid, but what we want to do is we kind of want to, just so all the methods that we know about solving simultaneous equations, we kind of want to write it in the form, say these are normal equations. So you have some coefficient times x plus some coefficient times y equal to some constant, say, and another coefficient times x plus some coefficient times y equal to some other constant. So what we want to do is we want to write these in this kind of form where you got all the this is actually something like you did in chapter 1, all the variables on one side, all the constants on the other. So this is what we're trying to do. So if you do that here, what you would do is you would add the x, take this away from both sides, take this away from both sides, add this to both sides, and what you'll get is s, x of s, minus a times x of s. Now we're trying to get all the x's and y's on one side, so take away b times big Y of s, and then, now this is some known number x0 in any example, so this is little x0 equal to x0, and then do the same for this, get all the x's on one side. Now we'll get them all on the left hand side, so take this away from both sides, you get minus c times big X of s, you got this plus s times big Y of s, what have we got, minus d times big Y of s equal to, this is little y sub 0, this is y0. Okay, so here we've got all the x's on one side, all the y's on one side, and the constants on the other side. So what we want to do now is get all the x's together, get all the y's together. So let's do that. So if I take out the x of s out of these, I have x of s times s minus a. So do that the other way around. You get s minus a times big X of s minus b times y of s equal to x0. And here you have how many x's, minus c times x of s, and then how many d, take y of s out of these, you've got s minus d of them. Simultaneous equations. Now you can go at these, so you'll see this in the examples, you can go at these however way you want. What I recommend is that you write these as a matrix equation. So this would be, change color, s minus a minus b minus c s minus d times x of s, y of s equal to x0, y0. So you write it as a matrix equation. Now I said you can go at this whatever way you like. Okay, so what's going on? So what I'm trying to do in this video is give the big picture. The big picture is that you've got simultaneous differential equations, apply the Laplace transform to both of them, and you can write them as simultaneous equations in big X of s and big Y of s. You can solve these simultaneous equations however you want. My recommendation is that you use Kramers Rule. So if you remember Kramers Rule from actually last semester, so it would say that dx, for example, excuse me, this does not make any sense yet. X of s, excuse me, would be equal to ds over d. Now what the hell are these things? So ds is the determinant of the coefficient matrix. Okay, and then what you want to do is ds, sorry, not ds, dx is the same determinant, but you replace the x coefficients with the constants. So the y stuff stays here, but replace the x coefficients with the constants x0, y0. And do you remember how to calculate these? Do this by this, right down diagonal, minus this by this. And this by this, minus this by this. And what you end up with is a so-called rational function. The thing on top will be some, it'll be, now looking at it here, it'll just have one s in it. And the thing on the bottom will have an s squared in it, so this would be a q of s. And this thing, you want to send this back. You look in the tables, is it there? No, usually. So what you have to do is write this as a sum of simple things that is in the table. So what you have to do is you have to factorize the bottom. Now I think there's two different types of examples that we look at. In one of them, it comes out already factorized, if I remember correctly. The other one is just a small, you get a small thing happening with the other one. So let me see. So basically this is just something to send back, and then you do a similar story with y of s. You use Kramers Rule again. So just the little things to look out for. Say, for example, big X of s. This is one that tends to happen. So let's say P of s will be some multiple of s plus a constant. And the kind of thing you're looking at is, say, s plus 2, s plus 3, minus 6. This is the typical thing that happens in these questions. Because look at the bottom here, it's like s minus a times s minus d. Now in context, the a and the d are negative, so these both to be positive, and then the b by the c giving you the 6. So this is kind of typical. So the issue is, how do you do partial fractions with something like this? So the first step is factorize it. This looks factorized. But it's not. It's not two things multiplied together. So if you want to factorize something like this, you have to be careful. What you have to do is multiply this out. So if you carefully deal with this, you get s by s is s squared, s by 3 is 3s, 2 by s is 2s, plus 2 by 3 is 6 minus 6. The 6 minus 6 gives you 0, and you have s squared plus 5s. And then this can be factored, and so you get s times s plus 5. And so in this case, the x of s is equal to some multiple of s plus a constant over s times s plus 5. And then if you look at this, this is a rule 1, this is a rule 1, and so you can do the cover-up method here. Yeah, that's probably the only thing to look out for. In my mind, the big picture is the more important thing to understand here, that you understand you're taking the Laplace transform of two simultaneous differential equations and you're ending up with simultaneous algebra equations. And the best way, in my opinion, is to go at it using the Kramers Rule. And what happens is, because Kramers Rule says y of s is dy over d, you will already, so the bottom of this is this d, it's going to be the same thing. You'll have found that in the first question. So what I mean by that is, once you find x, there's a lot less work to do to find this. So dy will be different, okay, in fairness. So dy, going back to the abstract example, the d is the same, say q of s, in this case s times s plus 5. dy, go back to here, you find the determinant of this, but replace the y coefficients with the constants. So you get like s minus a minus c, and then replace the constants minus b, sorry, that's wrong. So replace them with x0 and y0. Okay, so that's the general theory. Maybe we'll just mention very briefly what to look out for with the two applied problems that we look at. So the first one problem that we look at in the notes is brine tank cascade. Now the notes describe what that is. I'm just going to focus on the abstract actual equations. So they take the following form. You have dx dt is equal to minus some constant, I'll just call it a, times x of t, and then dy dt turns out to be a x of t minus b y of t. So if you do the Laplace transform on both sides, well, really what will happen is the following. You should notice that this is a function of x alone. This is actually quite easy to solve. And in particular, if you use Laplace transforms, in the middle you will find x of s. Okay? You will find, okay, so you'll find that if you follow this through, I think x of s turns out to be something like, be a little careful here, but I'm fairly sure it turns out to be x0, which is the initial value of x, over s plus a, and of course that goes back to, in the inverse Laplace transform, x0 times e to the minus at, and that goes to 0. You'll see me writing this in the notes as time gets big. And if you read what the brine tank cascade actually is, that'll make good sense to you. Now what you do then is, so the idea with this is, while this is simultaneous equations, the first one is a function of x alone, so you can actually just solve this. This one is a simultaneous equation, but after you've done the Laplace transform, which will give you s times big Y of s minus y of 0 equal to a times big x of s minus b times big Y of s. The idea being that you substitute this in here and you end up with, it's just an equation with Y of s, and if you actually carry it through, if you understand that, it actually turns out to be quite easy. It'll just be Y of s ends up being, well, let's just kind of roughly say what it is. So Y of s ends up being some number here, and you get some, say, q of s, and you get another term over here. This will be, the other term will be something like, I think it comes out to be s plus b, something like this. This is easy to send back. It'll be go to d e to the minus bt, and this just needs a cover-up rule. And what you get is two exponentials, and they both go to 0. Okay, so that's what's to be expected in that example. The other example that we look at is heat exchange problem. Now, so what that means here is that you don't actually need Kramers Rule. You can do Kramers Rule, but it's kind of an overkill. This one you will need Kramers Rule, and eventually what will happen is you will get down to x of s is some function of s over s times s plus a. You will get this. You do the cover-up method, you'll get some constant over s plus some constant over s plus a. Very easy to send this back using the inverse Laplace transform. This goes back to some constant plus b e to the minus at. And the thing to note is that as time gets big, this gets small. So as time gets big, the temperature, because x will be the little x of t is the temperature of one material, goes to this constant a. And then when you look at the other y of s, you end up with a similar story. Y of s ends up being the same constant over s plus or minus some other constant, say c over s plus, and some other constant, say b. This gets sent back to by the inverse Laplace transform, say a minus c times e to the minus bt. And this also, as time gets big, goes to the constant A. And what you see is that if you kind of see what this question is all about, these are X is the temperature of one object, Y is the temperature of another. They're in thermal contact, and what happens is eventually their temperatures will equalize. And this constant A here is the temperature that they equalize to. One of them will be initially hot. That would be this one, the plus one, and the other one is initially. Actually, that's. I think this is possibly the cold one. This is the hot one. This is the cold one. Because this goes down to A. This is the hot one. This goes up to A. This is the cold one. So that's basically the abstract of it. If you go and look at the notes, and again I apologize, just the thing went out of focus. This is what we're talking about.